The smallest altogether is this right there, and there's one in blue.
It's essentially like a family tree, but for plants. So it's a huge study that has involved sequencing the DNA of thousands of plant species to understand how they are related in what we call the plant tree of life. So it's the family tree of plants.
And carry on.
So by understanding accurately, as from this data set, how plants are related, this can enable us to understand how plants might have evolved and how they might have similar characteristics or properties that have enabled them, for example, to survive in their own environments, but also, again, to help us identify which traits are common to closely related species to help us with potentially finding solutions to many challenges that we have. So food security, drug discovery, climate change, conservation. So it's absolutely critical understanding robustly the plant tree of life. Because of this vast number of species, so 350,000 of the vascular plants, most of these we know have not been studied scientifically for drug discovery. And so the question or the challenge is, how do we know which of this vast number of species to investigate to find potential new medicines? So this is a huge mammoth task. So the project I'm leading at Kew aims to address this challenge by developing an artificial intelligence approach to predict which plant species would be more likely to contain lead compounds for drug discovery. The anti-cancer drug paclitaxel was first isolated from the Pacific yew, which resulted in killing many trees because it was sourced from the bark. And so scientists turned to a related species in the same genus and extracted similar chemicals from the leaves, which could be harvested much more sustainably and then converted into paclitaxel and other anti-cancer drugs in laboratory conditions. So this is a good example to show how important it is to find or to understand how plants are related, because then scientists can find more sustainable ways to derive medicines from nature.